Continuing with our study of integration by partial fractions, we're going to take a look at the case where we have irreducible quadratic factors in the factorization of the denominator. So in the case where the denominator contains a factor that is an irreducible quadratic term, that is a function of the form ax squared plus bx plus c, a quadratic function, where b squared minus 4ac is negative. Well, that means that this quadratic factor cannot be factored any further, because this b squared minus 4ac is the quantity that you would plug in the square root when you use the quadratic formula. So if it's negative, that means you have no real zeros for this quadratic function and it cannot be factored any further. So when we are in that case, then our partial fraction, our function r of x over q of x is going to have a partial fraction corresponding to this term of the form ax plus b over ax squared plus bx plus c. So at the top, instead of having just a constant, we have now a linear function. So let's take a look at an example. Let's say we want to integrate 2x squared minus x plus 4 divided by x cubed plus 4x. The first observation is that the degree of the top is already less than the degree of the bottom, so we don't need to do long division. So the next step is to factor out the denominator, which in this case factors out as x multiplied by x squared plus 4. X squared plus 4 is an irreducible quadratic term. We cannot factor that any further, at least in the real numbers, because it's x squared plus a positive number. Certainly it doesn't have any zeros. It cannot be 0. So according to what we have seen, the decomposition into partial fractions for this expression is going to be a over x, which corresponds to this non-repeated linear term x here, and to this corresponds a over x as a partial fraction. And then to our irreducible quadratic term x squared plus 4 corresponds the partial fraction bx plus c over x squared plus 4, according to what we just have seen. So now we need to find ABC, and to do that we're going to simply rewrite the right-hand side as one fraction. So in the first fraction we need to multiply top and bottom by x squared plus 4, so we get a times x squared plus 4. And for the second fraction, we need to multiply top and bottom by x, so we get bx squared plus cx. So now we have two fractions with the same denominator. That means that the numerators are equal. So 2x squared minus x plus 4 is equal to a multiplied by x squared plus 4 plus bx squared plus cx. We have an equality between two polynomials of degree 2, and these polynomials are equal if the coefficients of corresponding degree are equal. So we're going to rewrite the right-hand side in standard form for a polynomial. That is, we look at the terms in x squared together, the terms in x together, and the constant term together. For x squared, you see that we have ax squared plus bx squared. So the coefficient of x squared is a plus b. The only term in x is cx, and the only constant term is 4a. Now, this left-hand side and right-hand side are equal if a plus b is 2. In other words, the coefficient of x squared is 2, like on the left-hand side. C has to be negative 1, and 4a has to be 4. What that means is that b is 2 minus a while a is 1, and c is negative 1. And since a is 1, 2 minus a is simply 1. So we have found a, b, and c. And what we had is that the decomposition into partial fractions was a over x plus bx plus c over x squared plus 4, where a is 1, b is 1, and c is negative 1. So we obtain 1 over x plus x minus 1 over x squared plus 4. So this is what we're trying to integrate now. And of course, the integral of 1 over x is simply natural log of absolute value of x. And to integrate x minus 1 over x squared plus 4, we're going to split that fraction in two pieces. We have x over x squared plus 4 minus 1 over x squared plus 4. Now in the first fraction, x over x squared plus 4, we're going to integrate that by substitution, observing that if u is x squared plus 4, then du is 2x dx, so that the top x dx in our integral can be replaced by 1/2 of du. And so this integral becomes 1/2 of integral of du over u. And on the other hand, for the last integral, we can use this formula that gives us the integral of an expression of the form 1 over x squared plus a squared, or in other words, 1 over x squared plus a positive number. And as we have seen, this is a formula that we have established earlier in this course. This is equal to 1 over a arctangent of x over a up to a constant. So we obtain natural log of absolute value of x plus 1/2 of natural log of absolute value of u, but u is x squared plus 4, which is positive, so we get just 1/2 natural log of x squared plus 4. And then for the last integral, we simply have something that matches this formula in the case where a is 2, so we get 1/2 arctangent x over 2 up to a constant. Now you see that the key here was to split this fraction into two parts and deal with the first one by substitution, observing that the top, which is just a constant multiple of x over x squared plus some positive constant, then the top is a constant multiple of the derivative of the bottom, so we can take u equal the bottom and then use substitution. And for the second part here, we end up with a constant over x squared plus a positive constant, and we can use this integral formula with arctangent. So this method is going to apply in general to these kinds of partial fraction ax plus b over ax squared plus bx plus c, where the denominator is irreducible, that is b squared minus 4ac is negative. Now, it's not quite clear under this form that this approach can be applied to this, because we don't have at the denominator something like x squared plus some positive constant. But we can make it so by factoring, by completing the square at the bottom. So how do we do that? When you complete the square at the bottom, you're going to start by factoring the coefficient of x squared, and then complete the square for x squared plus b over a x. What does that mean to complete the square? Essentially, you want to write that as a difference of squares. Namely, you want to match x squared plus b over a x with something like that, the square of a sum. X plus alpha squared, if you FOIL things out, you get x squared plus 2 alpha x plus alpha squared. And we're going to try to match our expression with x squared plus 2 alpha x. In other words, b over a is 2 alpha, and therefore alpha is going to be 1/2 of this coefficient in front of x. And then we use the fact that another way to rewrite this formula is that x squared plus 2 alpha x is the difference of x plus alpha squared and alpha squared. So in doing so, we just replace x squared plus b over a x by x plus 1/2 of the coefficient in front of x squared minus the square of that term. Namely, this b over 2a is our alpha, and this negative b squared over 4a squared is simply the square of that alpha. So now, the next step is going to make our square x plus b over 2a, this quantity that we square, make it the new variable. So we're going to do a substitution where u is x plus b over 2a. Notice that in that case du and dx are the same, so that's not the issue. And then we can rewrite our expression as something like a linear function in u divided by something of the form u squared plus a positive constant, so something like alpha squared. Why is this constant positive here? Because you see that this negative b squared over 4a squared plus c over a is what my alpha squared would be, right? So this quantity here has to be positive. How do I know that it's always going to be positive? Precisely because if you write that as one fraction, The denominator, common denominator, is going to be 4a squared. So I have to multiply top and bottom by 4a in the fraction c over a. And I get 4ac minus b squared. So what I get at the top is b squared minus 4ac, which is negative. Sorry, I get the opposite of b squared minus 4ac, so I get something positive because b squared minus 4ac is negative. Now on the other hand, how do I get something, a linear function in u from ax plus b? Or simply by observing that if u is x plus b over 2a, you can solve for x and you get u minus b over 2a, and replace it here and you get the linear function in u. So, roughly speaking, modulo completing the square at the bottom and substituting for u equal whatever is the quantity that we square, we obtain a constant multiple of something of the form u over u squared plus alpha squared, plus another constant multiple of something of the form 1 over u squared plus alpha squared. This term is going to be dealt with by substitution, where I take v is u squared plus alpha squared, and at the top I have a constant multiple of dv. And this term is going to be dealt with using the formula we have seen with arctangent. So let's take a look at an example. Let's say we integrate 4x squared minus 3x plus 2 divided by 4x squared minus 4x plus 3. The degree at the top is not less than the degree at the bottom, so we have to start with long division. In that case, because we have the same degree, long division is something that you can do without really writing it out. Namely, you can write out what you need, 4x squared minus 4x plus 3, and then correct. Right? For the top to be 4x squared minus 3x plus 2, starting from 4x squared minus 4x plus 3, I have to add x to get negative 3x, and subtract 1 to get 2. In other words, now if I split the fraction in 2, I get 1 plus x minus 1 over 4x squared minus 4x plus 3. Of course, you would get just the same result just writing out the long division. You would get a quotient of 1 and a remainder of x minus 1. So now what is the next step? We have already our decomposition into partial fraction. The partial fraction now is x minus 1 over 4x squared minus 4x plus 3, where this is an irreducible quadratic term because if you calculate the discriminant b squared minus 4ac, you get 16 minus 4 times 12, so that's clearly negative. And so we need to go through the steps that we just described. In other words, we're going to complete the square at the bottom. And to do that, we start by factoring out the coefficient of x squared at the bottom. So I factor out 1/4 out of my fraction, and at the bottom I now have x squared minus x plus 3/4. And now I'm going to look at this x squared minus x and complete the square. The way we do that is just take x minus 1/2 of the coefficient of x squared. So that's x minus 1/2 squared, and then I have to subtract the square of 1/2, so I subtract 1/4. And negative 1/4 plus 3/4 is of course 2/4, that is 1/2. So we end up with this expression. Integral of 1 is x, then I'm going to pull out 1/4 out of the integral, and then I integrate x minus 1 divided by x minus 1/2 squared plus 1/2. The next step is to do a substitution where the new variable should be what's under the square. In other words, u is x minus 1/2. And I'm going to have to replace what's at the top in terms of u. So if u is x minus 1/2, x minus 1 is u minus 1/2. So I replace the top by u minus 1/2, the bottom by u squared plus 1/2. And now I do the same thing I have done in the previous example where I already had something of the form the square of the variable plus a positive constant. I split the integral in two. I get 1/4 integral of u over u squared plus 1/2. And then on the other side, minus 1/2 times 1/4, negative 1/8 of the integral of du over u squared plus 1/2. The first one is going to be dealt with by substitution, where we take the bottom for the new variable. It's u squared plus 1/2. dv is 2u du. So the top u du is 1/2 of dv. When I multiply by 1/4, I'm going to get 1/8 of integral of dv over v. And then for the last integral, we're going to use our integral formula using the arctangent. And we are in this case where a is square root of 1/2, in other words, 1 over root 2. You see that in the formula we use 1 over a, and of course 1 over a in this case is going to be root 2. So we end up with x plus 1/8 of natural log of absolute value of v, but v is u squared plus 1/2, so it's positive, so we don't have to worry about the absolute value. And u was x minus 1/2, so we end up with x minus 1/2 squared plus 1/2 inside our natural log. And then for the last integral, we apply our formula where 1 over a is root 2, so we get root 2 over 8 arctangent of root 2x up to a constant. Now in the next video, we're going to look at the case where these irreducible quadratic factors may be repeated.